Section 6.2 Orthogonal sets. We start with the definition. A set of vectors u1 to un is said to be orthogonal if each pair of distinct vectors from that set is orthogonal. Orthogonal means perpendicular. So the set is orthogonal if each vector, so u1 is orthogonal with u2, it means it's perpendicular to u2. u1 is perpendicular to u3, and so on. So each pair of those vectors needs to be orthogonal to each other. What does that mean? Two vectors are orthogonal if their dot product is equal to 0. Let's recall that the dot product is dot product of two vectors. Dot product of two vectors is nothing else but u transpose times u, right? This is the dot product. U dot product u is vector u1, let's say u2, is the first vector transpose, so it would be row. So it's vector 1 times vector 2. So we will write one vector times another vector. And then we would multiply the entry-wise this times this, plus this second entry times the second entry, plus the third entry times the third entry. That's the definition of the dot product. So we have example, determined if the given set is orthogonal. So the first part A, we need to check if each two vectors are orthogonal. That means if they are perpendicular. So to check if two vectors are orthogonal, we need to check the dot product. So we have vector u1 dot product u2. We take the transpose of the first vector times the second vector. So we would multiply 0 times 1 is 0. And then 1 times 0 is 0. We would add them. And 0 times 1 is 0. So this equal to 0. Since the dot product is 0, that means the vectors are orthogonal. And then we repeat this process for the next. So now I'm checking vector u2 if it's orthogonal to u3. So I take dot product. We pretty much multiply entry-wise. 1 times 1 is 1. 0 times 0 is 0. 1 times minus 1 is -1. That's the same row times column. We would multiply 1 times 1 is 1. 0 times 0 and 1 times -1. So it's 0. That means vector u2 is orthogonal to u3. Then we take dot product of u1 dot product u3. So first we check those two, then we check those two, and at the end I need to check first and the last one. So we check dot product or orthogonality of each pair. Each two needs to be orthogonal. So dot product of u1 dot product u3 is equal to, and we multiply row times column, vector 1 times vector 3. When you multiply them out, we get 0 plus 0 equal to 0. So indeed, u1 is orthogonal to u3. That means the set is orthogonal because each pair is orthogonal. Each vector is orthogonal to each other. Now we would do exactly the same for part B. We check the vectors W. So first I'm checking W1 dot product with W2. So it's vector 1, 0, 0 times the vector 0, 1 over root 2 and -1 over root 2. I think we forgot to have negative here. So this should be negative root 2. Because we have negative root 2 right here. But that does not change the fact that when I multiply this, I'm getting 1 times 0 is 0, and 0 times 1 over root 2 is 0. 0 times minus 1 over root 2 is 0. So when I add them together, the dot product is 0. So if the dot product is 0, that means vectors are orthogonal. Now I will check. Oh. Now I will check vector 2, u2, dot product u3. So the vector u2 was 0, 1 over root 2 minus 1 over root 2. And I will check with vector 3, which is 0, 0, and 1. And now when I multiply this, 0 times 0 gives me 0. 1 over root 3, root 2 times 0 is 0. But the last one, negative 1 over root 2 times 1 is negative 1 over root 2. So when I add them together, I will not get 0. So I can conclude that vector W2 is not orthogonal to W3. So what that means, if you find a pair that is not orthogonal, or two vectors that are not orthogonal to each other, you can conclude that the set is not orthogonal. Now we have theorem that if S is the set of vectors, is an orthogonal set of non-zero vectors in Rn, then S is linearly independent, and hence it is a basis for the subspace spanned by S. So orthogonal set is always linearly independent set. And if we have span, then if you have linearly independent and span, that's a definition of basis. So then this would form the basis. So here's justification of that theorem. So if I consider C1, so to show linear independence, I would need to show C1 U1 plus C2 U2 plus C3 U3. I'm doing this for 3 vectors, for non-zero vectors and some scalars C1. And we know in order to be linearly independent, those scalars must all be 0. So if I consider this equation and I apply dot product, multiply simply this times u1 times u1 times u1. In other words, I'm multiplying left side times u1 and right side times dot product u1. So then we can distribute the dot product. So it comes that we have C times u1 dot product u1, C2 u2 times dot product u1, C3 times u1 dot product u1, and 0 times dot product u1 is 0. So now we know that the vectors are orthogonal. If they are orthogonal, then the dot product to each other is 0. So this is 0, this is 0, but not dot product to itself. That would be the length. So the length square actually. So this is non-zero vector, so the dot product is not 0. So since this is 0 and this is 0, what I am left with is my C. I'm missing C1 right here. So here we should have had with C1 from the beginning. C1. Then we have, I'm left with C1 U1 dot product. And as I said, because the vectors are not 0, we have non-zero vectors. That means the dot product of itself cannot be 0, because dot product is 0 only if the vectors are 0. So then that means in order that this whole thing be 0, having this non-zero, that means C1 must be 0. So if we have first 0, then we would repeat the same process for all the other vectors. So I would do exactly the same for the other vectors. So I would start with this equation, then I would apply dot product of C2. So I would have C1, I'm sorry, U2, U1 dot product U2 plus C2 U2 dot product U2 plus C3 U3 dot product U3 equals to 0. So then exactly the same, because they are orthogonal, so those ones, this would be 0, dot product must be 0, and I'm sorry, this one was U2. So then U3 is 0. So what we are left is this part, which would be C2 U2 dot product U2 must be 0, because this is non-zero vector, so this cannot be 0. So in order that this whole product is 0, C2 must be 0. So this is how we would show that all the other vectors. So I have C2 0, C1 0, and I will repeat exactly the same, get the dot product, multiply times U3 to get C3 0, and so on. So now we have definition and orthogonal basis for a subspace W is a basis for W that is also an orthogonal set. Orthogonal basis for a subspace W is a basis for W that is also an orthogonal set. So orthogonal basis must be a basis that is orthogonal. So each two vectors must, dot product must be 0. So let W be the span. So if I have a span, and we show in the first example that this exactly this example above, that exactly the same vectors are orthogonal. Orthogonal vectors are linearly independent, and I have span, so that means this is linearly independent. That means that this is a basis, and because we show its basis and it's orthogonal, we call it orthogonal basis. Now the question is the above set of those three vectors also an orthogonal basis for R3? And because we have three vectors orthogonal, so that means linearly independent, and any linearly independent set of three vectors spans R3. So that means it's a basis for R3 and it's orthogonal. So indeed, it is an orthogonal basis for R3 as well. Now, every vector can be written as a linear combination of vectors from the basis. So the linear combination considers some vector y, and we write as a linear combination means some number times vector plus another number times the second vector and so on. So C1 are numbers and U1 are vectors from the basis. That's a linear combination. Now, if that basis is orthogonal, then it's very easy to compute the weights. So the numbers C1, C2, we can easily compute. And here would be how. So we consider let U1 be the orthogonal basis for R3. Then any vector Y in R3 can be written as a linear combination of vectors from that basis. So that Y we would write some C1 U1 plus C2 U2 and so on. We're gonna apply dot product on the right. So I'm applying dot product of U1 to left side and to the right side. To the right side, I would do to both of them. And then I would distribute the dot product by properties of dot product. Here, if you would like to see it, I would multiply here times dot product, and then I would multiply all of that times dot product of U1. And by properties of dot product, we can pretty much distribute this dot product. And then we have the next line right here, C1 U1 dot product U1, C2 U2 dot product U1, and so on. And as we talked before, we know that because the basis is orthogonal, so that means dot product of U1, U2 is 0. That means any two are 0. So if those two are 0, I am left only with that equation. So I am left with this part. So I am left with those two. And in that case, I am left with y dot product u1 is equal to c1 u1 dot product u1. And from this, I would like to solve it for c1. Dot product is a number, so I can divide by u1 dot product u1, divide by u1 dot product u1. This would cancel out. So I have c1 is equal to this part, which is written right here. And we know that dot u1 dot product u1 is norm square, right? We had that the norm of u1 is square root of those of the numbers, right? u1 square plus u2, or the coordinates. So we would need to denote them differently because this one is u1, u2 square, and so on. So if I square both sides, I would be left with this part, which is dot product u1 dot product u1. So the norm, or the length squared, is equal to u1 dot product u1. If you think of u1, I should have shown pretty much on the vector u. Okay, so that's how we compute the weights, and we can do the same process for dot product, apply dot product of u2 on the right, and then apply dot product on 3. That's how we compute all the coefficients, c1, c2, and c3. So this would be, in general, we have this one right here. If you have orthogonal bases, then each vector from that subspace is a linear combination of those, where the weights, or the scalars, are equal to this, what we just computed, c1, c2, and c3. And here is an example. So we have given the vectors. Maybe we should see it right here. Vectors u1, u2, and u3. And we claim that it's an orthogonal basis for R3. Now write this vector as a linear combination of vectors from that S. So y would be equal to some number c1 u1 plus c2 u2 c3 u3. And now c1 is computed according to this formula, or what we calculated before. So it's y times c1, the indices go accordingly, c1 u1 dot product u1. So y dot product u1, u1 dot product u1. So we take vector y and transpose it, and then multiply times vector u1. It's right here. And then dot product, it would be the same vector multiplied times itself. So then we multiply entry-wise. 6 times 0 is 0, plus 1 times 1 is 1, plus minus 8 times 0 is 0. The same we do on the bottom. 0 times 0 is 0, plus 1 times 1 is 1, plus 0 times 0, and we compute. And then we repeat this process for C2. That would be y dot product u2, u2 dot product u2. Go ahead, pause the video and do the calculation. Do the same for C3, and we should get this weights. So we calculate, this is the weights, so this is the number. Now we're gonna have it that the y is equal 1 times u1 minus 1 times u2 plus 7 times u3, and that's what we have right here. So we express it that this vector as a linear combination of vectors from the basis. But this formula we can only apply for orthogonal basis. If the basis is not orthogonal, we cannot apply that formula. We need to solve the linear system. This should also give us the same answer if we use the linear system. All right, now we have definition of orthonormal set, orthogonal and normal. So orthonormal set is a set that is orthogonal with all lengths with the unit vector. So the length of each vector is 1. Orthonormal means orthogonal set, but also each vector has length 1. Norm is 1. Length is called norm. So norm is 1. That's why the name is orthonormal. An orthonormal basis is a basis with orthonormal vectors, orthogonal vectors with length 1. Determine if the given set forms an orthonormal basis. So first we check if it's orthogonal, and then we calculate the length, if the length is 1. So to check orthogonal, we use dot product. So I call this U1, U2, U3 vectors. And first we check U1 dot product U2. So take the vector U1, multiply times vector U2. And if you perform the multiplication, indeed we getting 0. So U1 is orthogonal to U2. Do the same for U2 dot product U3. Perform it. You should get 0 as well. And U1 dot product U3. And you get 0 as well. So indeed the set is orthogonal. Now we need to find the length. So the length we calculate, check if each vector has length 1, the length we calculate square root of squaring the coordinates. So for U1, we take 1 square plus 0 square plus 0 square, which is square root of 1 is 1. 2, we would square each coordinates, and indeed all of them has length 1. So the length is 1. If you have orthogonal set with length 1, we call it orthonormal. So the given set forms orthonormal basis for R3. Now, if we have an orthogonal basis, we can always change it to orthonormal by normalizing the vectors. That means dividing each vector by its length. So we have examples. Determine if the set of vectors is orthonormal. If the set is only orthogonal, normalize it, so rescale it, the vectors to produce an orthonormal set. So first we need to check orthogonality, so if they are orthogonal, because if the vectors are not even orthogonal, they cannot be orthonormal vectors. So check orthogonality by checking dot product. So dot product, we take the first vector, multiply times the second vector. We have minus 1, 6 plus 1, 6, which is 0. Vectors are orthogonal. Now we calculate the norm. Norm means length. So we take U1, first one square it, plus second square it, plus third square it. 1/3 square it is 1, 9, plus 1, 9, plus 1, 9. 3 nines, which is square root of 1 over 3. We can distribute, it's 1 square root of 1 square root of 3. And this is 1 over root 3. And I will leave it like this for now. I repeat the same. Find the norm or length of U2, norm or length of U2, square the coordinates. So if I do it, I have 1/4 plus 1/4 is 2/4, which is square root of 1/2, which is 1 over root 2. So the length is not 1. And the question says, if they are not orthonormal, normalize it. So to normalize it means divide by the length, or create the vector with the same direction that has length 1. So to normalize the vector U1, we would take the vector divide by the length. To divide by the length is 1 over the length times the vector. So that's what I'm doing here. 1 over the length, my length is 1/3, 1 over root 3. So I have 1 over root 3 times the vector. So to divide by a fraction means multiply times its reciprocal. So I have 1 times root 3 over 1 and times the vectors. Then we distribute the scalar to each and every one, and that's this vector. So this is normalized vector. You can check that the length of this vector is 1. very easy and straightforward to check it, that the length indeed is 1. We would take square root of, we would have root 3 over 3 square root plus root 3 over 3 square root plus root 3 over 3 square root. So I'm having 3 nines plus 3 nines plus 3 nines, taking square root of that. So that would be 9 square root. So it's square root of 1. The length is 1. I'm showing that what we did is correct. We normalize this vector. So that means the length of that vector is 1. Here's the simple calculation for that. Now I'm rescaling the second vector. So I take 1 over the length times the second vector to 1 over square root of 2 times the second vector, it's root 2, and exactly the same. So now I have two the same vectors in the same direction and rescale it. So we have orthonormal vector set of vectors. If you rescale it, the orthogonality is preserved. And why is that? That's very straightforward to show. So if I have two vectors, u1 dot product u2 is 0. So that means those vectors are orthogonal, right? Now I multiply this, let's say, times 2. So 2u1 vector, if I take dot product with u2, I can take any scalar. I'm just showing for 2 to simply see it. By the properties of dot product, this would be 2u1 dot product u2. So if those two vectors are orthogonal, it's 0, and a scalar multiple would be 0 as well. So if I rescale those two vectors, orthogonality is preserved. It stays the same. So now we have theorems that talks about matrix U has orthonormal columns if and only if U transpose U is identity, orthonormal length 1, so it needs to be 1. If you multiply those two matrices, you indeed get identity. Here is a theorem that says about orthonormal columns. Then if you take norm of any vector that U acts as an identity, with orthonormal is norm of the vector and dot product and all of those properties. Because we barely gonna use this theorem, I'm gonna not spend too much time on it. Now we have orthogonal projection, and I think it would be nice if you pay really attention. This orthogonal projection, we will use it in this section and in the next two sections. So let's make every effort to understand this. So we have like this, given vector y is projected orthogonally on U. So if you have a vector, let's say this is my vector y, I'm projecting this onto this vector, I call it vector U. Orthogonally means you have a light and you shine straight light down. If you do it perpendicularly, orthogonally, that means you're gonna get shadow right up to here. This is gonna be your shadow, right? You can do it not orthogonally if you have a vector here and you project. If your lights shine this direction, your projection would be different. So this means that the lights are not perpendicular to the line we're projecting. That's why it's not called orthogonal projection, right? Orthogonal means light needs to go straight down and get straight image of that. All right, so if I have, need to redraw it. So if I have this vector y and I'm projecting this to the vector u, this is my original vector y, this is my u. I'm projecting straight down, my light is shining straight down, I'm getting image right here. So this is my projection. I'm gonna call it y hat. Okay, so I'm gonna call this y hat and note two things. That if I'm projecting straight to this vector y, that means that this vector, my projection, I call it y hat, and vector u, they are scalar of each other. So we can see that this y hat is, let's say, 1/2 of 1/3, in my case, in 1/3 on that drawing. It's some scalar. I'm gonna call the scalar alpha times the vector u, because I'm projecting. The same would happen even if you have a bigger vector and you're projecting on the small vector. You're still shining straight down lights, so your image would be right here. So the same story happened, then it's gonna be twice as big. In that case, my scalar would be 1/2 of 1/3, but here would be 2 or 3/3, okay? So the projection is always a scalar of the vector you're projecting on. Now, I'm gonna draw another vector that is perpendicular, and I'm gonna call it that vector z. Please note that y, if I add y hat plus z, it's equal to the vector y. So that's what we have right here. My vector y is y hat plus z. If I solve it for z from that, I subtract y hat, so z is equal y minus y hat. On the other hand, the y hat is some scalar multiple of u. That's what we explained right here. So then take this and substitute to y hat. So we are getting that z is equal to y minus alpha u. Now note that u, this is my u, and z are perpendicular because the z was chosen that way. Z is perpendicular to y hat and perpendicular to u. What does that mean? That the dot product of z times u is equal to 0. And substitute what was your z? Z is y minus y2, so I'm substituting right here for z. And then I use the dot product, I distribute dot product, so I'm getting y dot product u minus alpha u dot product u, and in that case I can solve it for the alpha. So this is my scalar of the projection. So my projection vector from the beginning was my y hat was alpha u, and now you can substitute for that alpha right here. So this is the projection vector. So this is projection of vector u, vector y. We're projecting vector y onto the vector u. So this is the orthogonal projection. And if we move, so this is written exactly the same what we had. Orthogonal projection of y onto u is a vector y hat such that projection y hat is equal y dot product u is projected onto this. So now we have example, let y and u, given two vectors, find the orthogonal projection y hat. So we simply apply the formula. So this is my scalar. So first I'm calculating the scalar, y dot product u, take vector y, multiply times u, and u dot product u, perform the calculation, 2 times 4 is 8, plus 3 times minus 7 is negative 21, and the same way. So this is the scalar, negative 1/5. So the projection was the scalar times the vector u. So I have negative 1/5 times this vector for negative 7, and that's my projection vector. So y hat is my projection. Now, part B asked me to find this write the y as the two orthogonal vectors, one from span U and one from orthogonal U. Span U is scalar multiple. What is span? It's all scalar multiples of the vector U, or linear combination of U, or just scalar multiples. So vector in span U Vector in span u is nothing else but some number times u, some number times u, or you can say alpha u, or nothing else but y hat. So the vector in span u is my is my projection. But now another vector orthogonal to u. What vector on my diagram is orthogonal to u? Nothing else but z. So this orthogonal to u vector would be the vector z. So how do we calculate this? We know that the orthogonal projection plus z is y. Solve it for z, y minus yu, and that's how we find this vector z. So in that case, the vector y is equal to y hat plus z, where y hat is the projection and z is this vector. I can show you one more time how was it to understand this one. So we have the vector y, we project it onto z, I'm sorry, onto vector u. So this vector was called y hat. It's this vector right here, and this is vector z. So we see that y hat plus z is my given vector y. From that, I'm solving for z. So z is y minus y hat, and that's how I get all the calculations.